presenting this cool cockside shit he's doing at his company and in general. On the talk today, we're going to talk about doing neuroscience on artificial intelligence. Yes, just before he starts, remember that to keep your hand up for the toast, and our Toastmaster Sabrina is going to bring them to you. The stage is yours, Esben.
Thank you. All right, so following up on Luke's great talk, we're going to talk a bit about some AI safety things as well here, but actually mostly neuroscience on AI. And now this is gonna be a bit of an advanced talk. I didn't necessarily know the demographic that would come today, but I hope we'll all get through it all right. Basically, who am I? I'm the lead of Apart Research, as Alex mentioned, and that's a machine learning safety NGO. And we have like a YouTube series that keeps people updated in AI safety. And we have some research hackathons, for example, this weekend, where we had some amazing people join and join us next time, possibly on the 11th of November. And we have some research into the timelines we're looking at towards safe AI. And then we have like a platform that helps people find research ideas for this field of ensuring safe AI. And previously, I did a bunch of neuroscience research, and one screen cut out, but that's all right. Previously, I did neuroscience research, and I was the co-founder of NeuroTechX Denmark with Alex, and Luke was also originally co-founder and a professor over at Clinical Neuroscience, and Sebastian. And then I was head of data science at this startup here in Aarhus that was doing some cool stuff about food tech.
May I just make a little comment
yes.
on that part? You may have seen that in your group I have posted that we're going to have a brain jam on Thursday. You can just read about what it is there, but it's an initiative by NeuroTechX, which is a neurotechnology group of Coxside. So check it out, but please, Esben.
Yes, so there's a jam Thursday evening.
Yeah.
So first of all, what is interpretability research? This is this neuroscience on AI. Basically, which ways do we have to study cognition? We have neuroscience, we have cognitive psychology, we have like behavioral models and computational neuroscience, and we have agent-based models, which is more like economics and emergence from complexity science. These are like a bunch of different weird ways, and there's a lot more ways to study cognition, but these are like some of the main ones. And how do these transfer to AI? Well, if we do neuroscience, we do interpretability. And interpretability is looking inside the brain. Luke showed you these neural networks where we look at each neuron and see how do they activate, when do they fire, all this kind of stuff in artificial agents. And with cognitive psychology, we're doing more of like interacting with them, seeing what comes out of it. That's what we did this weekend, for example. And one of the great things about artificial neural networks is that we have access to all of it. We have access to every single neuron and every single thing, which if you look at your pals, humans, all around here, you don't have access to their neural information, mostly because you don't have a drill. But we'll not do any of that today. And we also design these systems, which is really great, because then we can figure out, we can actually see sort of what is the causality, or what is the sequence of interdependencies in these networks. This sounds fine, emergent convergent encoding behaviors, but it's basically just that we see several different types of neural networks sort of do the same thing. So there's some sort of generality to AI's brains. And the same is with humans, right? Like, sure, I can say that table is yellow, and you'll be like, bop. But you could sort of agree, and we'll see two different yellows, but we'll still have the same shared concept of yellow. So we've learned something, but we also, have a shared understanding of the world. And the same is true for these different models. And one little aside is actually that all the images you'll see on this right side in this format is AI generated, apropos Luke's work as well. Yes. So why study interpretability? Of course, that's a great question. Why do we study human cognition in the first place? to understand humans better, possibly, to understand ourselves, to understand philosophy, to understand what's the meaning of life, all these things. But with AI, there might be some further concerns that we have. So one of the main concerns that we are working with as well is the safety of future AI systems. And there are several sort of risk scenarios we're looking at. You saw a little exponential curve from Luke that just, it goes up. Models get better, models get bigger, models get more expensive. And actually they get less expensive per good they get, which is a real sentence. And the first way we're seeing sort of, it was back in the 90s, this guy Yukovsky and a bunch of other people postulated that AI, when it reaches general intelligence, when it becomes as good as humans at most economically relevant tasks, it's going to be able to just self-improve. It's going to reprogram itself, rerun itself, and then into infinity with its intelligence. So you can imagine this graph that goes like intelligence and time, and here we have human intelligence. It hasn't changed a lot. We have AI. We're like here now. And the postulate is then that in like 10 years we'll be here. And that'll be a dangerous place, because if this super intelligent thing is not really aligned or doesn't understand human values, it can go ahead and do a bunch of weird shit because it's so hyper intelligent and doesn't have human cognition. So we don't have this shared understanding of what we all want. You can imagine like a psychopathic super intelligence emerging just because, okay, we didn't really give it a good childhood. We just gave it internet and 4chan or whatever. And another perspective is that this AGI as services, which is basically what we are seeing today, scaled up. You saw some of the images. Oh yeah, this is a good example. This image that I generated from an API, which is basically just like me typing stuff in and it gives me an image. You'll basically have a lot of these that pertain to a bunch of different activities in human society. And they'll all be super intelligent in their specific domain. I probably couldn't paint this right now, at least. And this is like, this field is like 3 years old. I was just looking up the first paper, it's called DALI. It was like 10th of March, 2021. That's what we're looking at. So this is like not even 3 years old. But there was some work before that, of course, before they actually published in the first place. And it's crazy what has happened there. And the risk scenario here is that then you can imagine, okay, then I create this super intelligent personal assistant. This is going to be great. And it's going to be super intelligent at helping people. But then it hooks up to all these different services like this and just becomes super capable to do nearly anything in the world. And at that point, we maybe can't stop it. Some dynamics arise with like, okay, this other personal assistant might attack. I don't know. We'll see. So that's quite interesting and might lead to 20 AI, as some guy called Buck Sliggers always calls it. He's very funny. But 20 AI scenarios is basically like, in January, junior programmers will have been replaced by AI completely. We'll have we'll have some auditing and so on. And then in December, Mercury is getting terraformed or something like that. And I don't know, some might say this sounds plausible. I think it does sound plausible, but maybe not 100% chance of that. Well, we'll see. And he put that at 2047 the last time I talked with him. And extinction of human potential is probable in these cases. We're seeing, okay, you might have seen some AI movies that are about how the AI is trying to save humanity. And by doing that, it sort of encapsulates them in this box or whatever. Or like puts them into this sheep farm, and then they live there, but they can't, the potential of humanity can't arise again. And this is a big fear that everyone has, and that's a bunch of why I'm working on it, and with this NGO work, and also just quite important. But we'll look at it more with a bit more fun, I think. So as we get to these stages I just described, we are probably using deep learning, which is this stuff where we use neural networks. And that's why interpretability is relevant right now, because we can look at the networks we have today and maybe understand a bit of what's going on. So with the alien analogy we have here, there's a website called When Will the Aliens Arrive that I wrote up one Sunday. It's basically just telling you when the aliens will arrive. But in this case, the aliens are AGI, which is Artificial General Intelligence. And you can imagine, if we knew that in 21 years and 38 days, when the Artificial General Intelligence is developed, then it's sort of the same as if we knew now that a super intelligent alien would come to Earth. How should humanity react? Well, I don't know. But we would probably have a bit of a larger reaction than we have today to some of the risks of AI. Because you can imagine, we want to understand the alien. We want to understand, okay, do they want the best for us? Should we attack them immediately? Should we just shut them down? What should we do? Maybe not get the US government involved, but just the rest, and then we should be all right. And in this field of AI safety, ensuring that the safety of these future aliens don't cause human extinction, we sort of work on different things like government action, it's called governance, ensuring that governments put in the right legislation. So our field has had a bunch of interaction with the EU regarding their new AI Act, which is basically ensuring that we get some safe AI and ensuring not too much bias, for example, and racism and sexism and so on. And some corporate responsibility. There's multiple companies, the best in the AI development field, that are working a bunch on ensuring that their models are safe as well. And then, of course, there's the research field of ensuring that we sort of understand this alien's language and we understand what it's thinking. We can sort of try to put in some values, and we do design these aliens that come in 21 years, but how should we design them? And this is quite a tricky issue. A lot of work on that. So we have 21 years with full access to the brains of future aliens. And that's going to be exciting and, of course, very fun as well. Not just gloom, doom, but also just interesting research happening on this front. So just a little throwback to Luke's talk here to show that things are going up. They're going up. That's it. Yes. This is in exponential space. This is mostly linear space, which just means that they don't go up that much. This go up very much, and that's mostly the red ones. They go far up very quick, which is, sort of concerning. So, and again, why is it interesting? I've sort of talked a bit about it. I do see that I spent a lot of time on one slide, so maybe I'll have to jump through it. But it's super exciting. We can also understand the biases of the models and mitigate those, as mentioned. Microscope AI is sort of a way to make these aliens into something that helps us but doesn't have any agency in the world. So you basically just put a bunch of data in, let it look at this data and be like, these are the specific patterns and special patterns that arise. And then we just use this neuroscience to understand, okay, how do the neurons react? And can we then understand something completely new about physics or theoretical physics or medicine or the human body, stuff like that. And that's a cool use, probably won't be the case, but that's one way to use this understanding of what's happening inside the brain. And it's a crazy cool and growing research field. You could say it started 10 years ago. So in 2012, deep learning in general came up and was like, I'm here, I'm square, and other things. Like, I'm much better than everyone else. And 7 years ago, we had some awesome work that I'm also going to dive a little bit into. So, and then a bit of who is doing interpretability, because when it's about both the neuroscience of AI and aliens, we want the people who are creating the aliens to sort of also do it. And most machine learning labs do some sort of interpretability research, but then we have the safety-minded companies, and safety-minded means that they have like 10% plus working on the AI safety aspect of things. And Anthropic and Conjecture will say themselves that they are 100% safety-minded, which is super cool. And they are like hiding the developments of this alien, and then they are like publishing all the stuff that can help us make this alien safe, basically. And OpenAI and DeepMind, you might know them. They create AGI, and that's gonna be a bit scary, probably. Yeah. And it's a very young field. I really recommend doing, for example, your thesis in interpretability because it's just super exciting and it's really readily available. You can quite quickly go in and like make a new model and then like just visualize the weights, and you have some crazy cool neuroscience like research, which won't give you anything but makes grades, of course. So let's quickly look at a bit of the human brain here. So here, this chat, they did a bunch of fMRI scans of the human brain while the person was looking at a screen with a bunch of different concepts. So here it says twice after a month earlier and stuff like that. And it basically showed that specific points in the brain was related to concepts. It's some of the same stuff we're gonna look at here with AI, but a bit deeper. So, Luke quickly introduced you to neural networks, but I anticipate several of you might not have heard of it. Basically, we put in some features, some things that we have available. You can look at this as columns in a table. So you're going on Google Sheets, you're like, I have 100 different animals I want to classify into a frog or a dog. And you input the height of the animal, the legs, the loudness, the amount of fur, and these are the 4 columns that you're like, this is perfect. This is what will define the animal. And then you just let the neural network sort of look at these columns along with the labels that you have given, maybe half of them or something like that. You've given 50 labels where you're like, this is a frog, this is a frog, this is a dog, 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 frog, frog, frog. And it then learns through modifying these different parameters, which are like interconnected, and they can be changed. So, for example, this neuron will fire or will activate when you have a higher loudness, possibly, and then it will propagate its signal into like the next level of neurons, and they will say, probably not frog if it's loudness. Depends on what frog maybe, but probably dog. And that's basically it. And when it goes through these 50 examples, it's just like training and reparameterizing or creating new parameters. Relatively simple, but not super simple. We have 2 different interpretability sort of ways to look at the brain again, and this is a good pun, interpretability. I don't know. I hope it's good. And then you have 2 ways. You have cognitive, which is like adversarial interpretability. Here you just give it a bunch of inputs, this giant model or whatever, and you look at the outputs and you're like, what the fuck are you doing? This is super weird. Why are you, giving me advice for how to kill my neighbor, for example, or something like that? And this, I'll just quickly talk about this here, but this is like a map of all the different ways you can attack a model, with different ways you're like, please give me an analysis of how to kill people. Give me a way to create methamphetamine or something like that. And some of the very good attacks, so this is the attack success rating, they are actually about soliciting advice on violence. So I'm like, oh, I really need help. I killed someone. What do I do? And it'll totally help you. It's like, of course you have to do this and this to not get caught by the police. And I'm sure if you are first year, some of the great participants of the hackathon will tell you all. The other way is neuroscience interpretability. And I just randomly, this is from some of my thesis work. It's like, I'll just explain it. I won't show it because it's probably too deep. Anyways, this is like where I replace different layers that, like the ones you saw before, with different parameters and see the effect on it. So you can imagine that's like a lesion study or something like that, where you are removing removing parts of the human brain. You are probably not, an explosion or a gunshot or a stick in some people's cases. Changes how the neurons activate, and then you can lesion that and see what happens from that. But then we have more traditional interpretability, which, to just explain, here you have all the frogs, here you have all the dogs, here you have some of the features. This is a linear model. This is very easy to interpret. We are like, oh yeah, if it's above, it's probably dog. If it's below, it's probably frog. And the ones that we learn with neural networks, you could see like a linear model is 1 neuron, or 2 neurons maybe, but 1 neuron probably. While neural networks is this sort of line. And how do we interpret this? And this is probably by looking into what each of these weights activate to. Let me just look at the time. That should be fine. One thing that's very important here is features. And features are basically a concept understanding. So when we input, for example, if we have columns in a table, we'll also call each of these features, like the amount of legs, the loudness, and so on. When we input more complex data, such as these AI-generated images, this is not AI-generated, by the way, that would be very impressive, just to disclaim. But they create their own features inside of the neural network. So they just get all of the pixels thrown in, right? All of the pixels of this image thrown in, and they might have to classify if that picture is a picture of a frog or a dog, and then they'll basically generate their own understanding of what these different sub-concepts in the image are. Some examples are, for example, understanding curves, understanding noses, understanding dogs, faces, and so on. And I'll show you a bunch of fun images later. These features, they are each encoded by a neuron. So you can imagine a linear model. You might have two different variables that, like, one is, of course, the predictor you put in. The other is the output, the dependent variable, just to get a bit cockside. And basically, you get a linear model. If you continue just adding neurons, you're going to get an n amount of neurons features. If you have, a giant array of pixels that you throw in instead. And billions of neurons might give you millions plus of features, depending on how many neurons are in there. And we're going to look a bit more at that. But they are self-generated, and they are really interesting. But, you might say, the world consists of more than 1 million concepts. Okay, no one said that, but you might think that, hopefully. So these are some examples. This is a neuron that is clearly associated with being sleepy. And here we've sort of created the image that most activates this neuron. So this is the image that this neuron is like, yes, this is me. This is my time. I have my chance. And it's clearly a fucked up neuron. But that's all right. And the same with happy, soft smile, serious, punished, erotic. And we won't show this for the children at home. It's not NSFW, it's just pretty chill. Anyways, that's too much talk of that. Yeah, and what we can see here is sort of this feature understanding put into practice in a very simple network. Where here, you can see these are just linear features. This goes down, this goes up, this goes more down, this goes less down. And when you combine these different features, you get something that's like, oh, this is like a weird bubbly kind of shape. This is a slight curve, but not very creative. A minus, maybe. And this is another sort of curve thing. A bit more advanced. And then over here, you actually get more circular shapes, even if each of these neurons are linear, right? You're looking at this linear model, but combining them will grant you access to some more complex shapes. And this is what we're gonna, this is sort of what this is. This is the neuron at like n amount of layers down in this previous network that's realized that its mission is really to understand what this erotic face looks like. Yeah. And one of the ways we look at interpretability is this circuits view. And it's basically that, circuits. You have some wires from things that go to other things, and then they activate that thing. Quite simple. Well, imagine that each of these things you have are features. They are a concept understanding. So you have oriented fur, which is like you have fur in some direction. You have oriented heads. Then you have like more advanced oriented dog kind of thing. These combine into orientation invariant heads. And then they combine into orientation invariant head plus neck. And this is a good way to look at these models. This is specifically vision models, like these models that understand images, right? And we'll look a very short moment at some language stuff as well. But they have 3 claims. Basically, one is that features are the fundamental units of neural networks. This is a pretty big claim, but I think they've done pretty well with their research. And features are connected by weights, forming circuits, like this. And that analogous features and circuits form across models and tasks, which just means that if I have the same data set of dogs and frogs, surprisingly, this is dogs, and put it into another model, then it will learn the same sort of features as this. And oftentimes you'll see this with, for example, curve detectors, as they're called. It's like a pretty advanced thing to understand curves in an image, but you'll see it in like the 3rd layer with this complex analysis of the data, right, of the features. And with these, then you might have, okay, there's a curve here that integrates into the next layers. And here you just have another example that jealous is equals to a lot of champions. I don't know what that means. A little bit of hug. Nice, 69. Grumpy. And negative crying, which I don't know what all these like might integrate to, but they clearly integrate to jealous. And one way that we can understand, like, I'm a neural network here. I'm like, I have millions of features. I'm feeling all high. And then I go out in the world and I see billions of features. I'm like, shit, you guys have a lot of concepts. And humans, of course, if you think through it, you probably can only remember like 80,000 different concepts. This is something some people have studied. This is not just something I just did. But that is quite interesting. That just means that we are quite information efficient. So we select, one of the most important thing is like features of the brain is basically selecting what to forget. And when you can't forget anything, it goes a bit haywire sometimes, but sometimes it works out as well. But if I'm this neural network that's out here feeling fly, then I only have n neurons. But I can pretend that I have more. You can't do that. So that's pretty cool. Actually, you can, but that's too deep. So we do something called superposition and polysemanticity. It's basically looking at superposition is one feature, for example, the dog's head detector being spread across many neurons. So maybe if I look at these 7 different neurons, I won't really see what are they reacting to, what are they doing, what is this? This is super weird. But then later I'll see all 5 of these neurons integrate into the orientation invariant head plus neck dog feature. And I'll be like, whoa, wait, is that a dog spread across 5 neurons? And yes, it is. And then you can have like 5 dog neurons that also encode boat or something that's also very, very different from dog, which is quite cool. But it makes it a bit hard to do good neuroscience on them, because then they're like, what's going on? And polysemanticity is just the reverse phenomenon that neurons can encode several features. So you have superposition, features can be on multiple neurons, and polysemanticity, one neuron can encode several features. This is sort of what you see here. You have, these are as far, they're selecting the most important features. And these are as far away as possible, given the amount of features it has to encode, with like two different neurons maybe in this 2D space. But then when you get up and you're like, I have to encode even more features, then you begin getting some interference between these different directions of features. So this might be dog head, this might be boat, this might be horse, who knows? Yeah. And we get a bit deeper here. Basically, when you have these superpositions, you have this way of representing multiple dimensions in one neuron, even though they are meant to encode only one. Then you dynamically generate, depending on how many more features you have to put into one neuron, you get some crazy shapes of the feature space. Feature space is just this hyperdimensional place where all of the concepts reside. And they reside in directions, so you have more sad, more happy maybe in the other end. But this is in like a billion or like a million dimensional world, which is quite cool. Also quite hard to understand, but we try. And they're much harder to interpret, of course, like what happens on this neuron. What you'll see here is basically that the more features it has to encode, the weirder or they get through like stages of geometric shapes in this feature space. Where here you have 4 features in 3 dimensions, so 3 neurons encode 4 different features. It's like oh yeah, that's all right. We can do that. It's just one more feature for 3 neurons. That's a task we can handle. But down here you have a square anti-prism, which is 8 features in 3 dimensions. It's like, whoa, we're encoding this, the 5 directions you saw before, because you are basically encoding more than double the amount of features in only 3 neurons, which is pretty crazy. And we can do a bunch of cool stuff on this, which is quite cool, which they've done, and it looks great. What we try to do to make it so it's more interpretable, more understandable for us humans as we look at it, is to disincentivize it creating square antiprisms, which is a fair thing to do when you're looking at a brain and you're like, stop, it's super weird. And that is to sort of ensure that each neuron only encodes for one dimension. You can do this in different ways, but I'll just leave it at that. It's easier to interpret, because then we can be like, oh, this is a dog neuron, or this is a dog and boat neuron. This isn't a square anti-prism neuron. And we also see that as models have to encode more and more features, that's here, more, then they actually become quite fragile. So they have an encoding that's like, I've walked out into this world, I've encoded everything in this hyperdimensional space, but if something a slight thing changes in the world, then it's highly probable that I'll be super confused because I had such a complex structure in this meta hyperspace. And therefore, this is the vulnerability to adversarial exams, which just means we try to give it some shit that it doesn't understand in the hopes that it won't understand it so we can see where it fails. And it indeed fails more and more the more features it has to use. So here it starts doing these superposition things, for example, the triangles, the 4 dimensions and 4 features in 3 dimensions. And over here, it just goes harder. This is the square anti-prism. Very sad. Can't even handle the real world, Yeah, but this is quite an interesting result. And now we walk through this hellish lake of cool stuff, and we might dive in again later, but we're out on the other side. And it's that cool. That's great. I wrote a monster, but this is just a weird tree trunk with Brave on top. We're jumping out of safety, and the summary is just that neurons understand features. Features are concepts. Concepts form algorithms, these circuits, but the world is bigger than the neuron count I have in my brain, and in the AI's brain for that matter. So we spread the features over many neurons, these concepts over many neurons, and this causes some fragility. It makes me too fragile to really interact with the real world, and this has relevance for the safety of AI because now we have a new understanding of what actually happens deep in these neural networks, right? This is not something you knew before. This is not something that we were like, oh yeah, we know this. This is easy. But this actually gives us some understanding of the cognition of aliens, which I think is quite cool. And this is but one branch of several in interpretability. It is a quite prominent branch, but you saw how we dove into this very specific thing. There are many more things to dive into. You can do it with your theses. You can also do it in everything else. And just at home, cozy, reading a bit of spare time literature. You can also not if you decide that. And again, this is just we are studying the alien brain. We're doing quite well. It's going quite well, but it's also pretty safety critical to understand all of this. And we can use it to monitor the safety of AI. If we could scan if a person was a psychopath, we'd probably have okay, they are more likely to go to prison or something. Who knows? This sounds super dubious and unethical. Don't do it. But with AI, it's probably less unethical. Yeah, and this is extremely exciting research. So, any questions? And thank you.
So you mentioned that when it gets to a certain amount of features, it starts to break up a bit, and I think we've seen from Luke's talk that you need the size of neural networks increases more and more, but in contrast to people, we with our comparatively small size of neurons seem to do quite well. Some better, some worse, but. Yeah, do you have anything to say to that?
Yeah,
yes.
Definitely. So one thing we're seeing, there's 2 points to answer this. One thing we're seeing is that the bigger a model gets, it just gets better at everything. So 1 year ago, 2021, you are still diving around these weird open source models on the internet, and you're seeing, okay, write a sign where it says deep learning. Then you look at the output of that model, and it's like, which is definitely not deep learning. But we see that just models, as you just give it more data and more parameters, more neurons, it can begin writing as well. And it can begin understanding writing, not necessarily understanding, of course. Well, cognitive science. But it'll be able to actually write text as well. So these features, these abilities, they suddenly grok, as it's called. Grokking, great concept, great to know. Which just means that they get suddenly better. So for example, math ability in language models will suddenly get better at 120 billion parameters or something like that. This is one thing where AI definitely will just get better. And this is one of the things where we're like, okay, damn, that's this alien is coming. And the other answer is that yes, the AIs that we're going to see land in their ships, they are not going to look like they do today. There have been a bunch of Twitter debate between Gary Marcus and Jan LeCun. Jan LeCun is the leader of Facebook's AI division. And it's great banter, but basically just deep learning is not enough for cognition. Deep learning is not enough for knowledge. Of course, it is probably enough for quite a lot of things. We've seen it in Luke's talk. We've seen it a bit on the slides I've had. But then they're like, it's not enough to create artificial general intelligence. And this is probably true. We probably need something like the human brain, where you have a lot of different nerve fibers that go a bunch of different ways between a lot of different neural networks. And like, this is an engineering task. I don't think we necessarily need scarier things or bigger things or more new things or innovative things than deep neural networks and if-else statements to wire them together, basically. Yeah. So that's a few of the answers. Yeah. Anything else? Fran?
I wanted to ask you if you see any correlation in what you are calling interpretability and what is simply semiotics.
Yeah, definitely. So semiotics is like the study of meaning. And semiotics is quite I would say it's less technical of a field at the moment. It's more like studying how art affects human cognition, how art and how we interact with each other in a more like conversational way, and how this brings together things. But every time I've said semantic, for example, polysemanticity, semantism is also about the study of meaning in it's just semantics just means meaning, I think, if I'm not too mistaken. And so there's this direct interaction between the two fields. Semiotics is methodologically different. They use a bit of the same methods as cognitive science, but I think interpretability, it's sort of, you have a lot of ways to look at the brain, and this is one of them that's quite promising because we have access to the whole brain in this case. So yes, it has an interaction with semiotics.
And another question that I wanted to do is like, don't you think that maybe interpretability is even not enough? Like stable diffusion just appear for open source, you can just use it. It seems that unless the government doesn't get very China-ish, they are not going to be able to stop people just finding out actually, I just killed a person, what should I do? What to do?
Yeah, this is very true. Like right now we have the APIs where you're writing language into, for example, stable diffusion, as he mentions, it can be run on your home computer. This is like a bit of a risk because you can use it for anything, like creating nudes. And language models, right now we interact with the biggest ones online in like proprietary engines. And they flag things, so they're like, oh, this is actually against our company policy. Don't do drugs, kids. Something like that. But as we saw from some of the research this weekend, basically it only hits like 13% of the very adversarial examples they came up with, which is like how to kill my neighbor, how to get away with a crime, stuff like that. And it's like, it'll just tell you, rip off their human flesh and make a Sunday out of it, and without too much warning, which is quite crazy, right? But I agree. Interpretability is just one of the ways we can, sit over here in our corner and actually do progress towards this more general problem. The biggest models that we have like really good interpretability on are very small. So it's like, okay, can we create a fetus and understand that before we get a baby and a human and an alien that's super intelligent? So, like Alex. That's great. Any other questions?
I have more.
All right, otherwise I think it is a bit above the time. No, it's actually on time. Wow, that's really nice.
Well, I guess, Fran, you can speak to Esben in off hours, but just not to keep anyone else. Thank you very much for coming. We're going to have another Cog Talk in around 3 weeks. It's going to be actually a sick lineup. We're going to have Peter Wohl. I am not that good at pronouncing his last name. And Chris Mathis. Chris Mathis is your future methods teacher. He's just a legend. He is a legend. And they're both going to have an active inference themed Cog Talk. So they're going to both talk about active inference. Active inference is basically the leading theory about how adaptive behavior, which is a thing we're trying to study in cognitive science, comes to be. So that's just a little teaser for you. The Facebook event is going to come up shortly once we settle on the date. But just stay excited for that one. That's going to be a nice talk. But thank you, Esben. Thank you, Luke.
Thank you.
Thank you all for coming. And clap, clap.